Picture the headline that circled the globe. Inside a golden chandelier, colder than the space between the stars, a machine is handed a problem. And in the few minutes it takes to make a cup of tea, it's finished. And they said, the mightiest supercomputer on Earth would have needed 10,000 years to do the very same thing. 10,000 years against a few minutes. So if that's true, the future has landed. The old machines are scrap. Every secret is crackable. Everything changes by breakfast. And there's only one question worth asking tonight. Are we there? Is that what just happened?
That's the question, isn't it? And I want to answer it honestly, the way we've tried to answer everything this season, even when the honest answer is less of a thrill than the headline. So here it is, plainly. No, we are not there, not remotely, not close enough that you should change a single thing about your life this week. And yet, and this is the part I love, that headline was not a lie exactly. Something genuinely astonishing did happen inside that cold machine. The trouble is that what genuinely happened and what the headline said happened are two very different animals. And telling those two apart, that's the whole of tonight. The headline that went around the world.
All right, I want both. I want to know what actually happened in the cold box. And I want to know why it isn't the thing I was told it was. Start with the machine. What was it doing for those few minutes?
Good. So a few years ago, a team built a processor, a chip with a few dozen of the qubits we've spent this whole season getting to know. 50 odd of them. Superconducting loops, the kind we met last time, sitting in the chandelier, near enough to absolute zero to be the coldest thing for light years. And they gave it a task. Now, I want you to hold on to the nature of the task, because everything hinges on it. They did not ask it to factor a number. They did not ask it to break a code, or design a drug, or solve anything anybody wanted solved.
What did they ask it to do?
They asked it to make a mess. A very particular, very beautiful mess. They fired a long, random sequence of quantum gates through the qubits, rotations and entanglings, one after another, chosen at random, stirring the whole thing into a fantastically complicated superposition. Every one of those qubits tangled up with every other, all those amplitudes we talked about sloshing and interfering, reinforcing here, cancelling there. And then, at the end, they measured, and out came a string of ones and zeros.
One string? After all that?
One string each run. Do it again, another string. Again, another. And if you run it 1,000,000 times and tally which strings turn up often and which turn up rarely, you get a very particular, lumpy pattern of likelihoods. This string common, that one vanishingly rare. A fingerprint. And that fingerprint is set by all that interference inside the machine. It's the signature of the quantum storm they stirred up.
So the answer is the shape of the mess, the pattern of which random strings come out more often than others.
That's it exactly. And here's the sharp point of the whole thing. That pattern is savagely, brutally hard for an ordinary computer to predict. To work out that fingerprint the honest way, a classical machine has to track every one of those sloshing amplitudes at once. And there are 2 to the power of the number of qubits of them. We met that monster back when we first talked about why simulating quantum systems is so hard. 50-odd qubits means a number of amplitudes with more zeros after it than you'd care to write. No ordinary computer can hold that in its head. So the classical machine grinds and grinds, while the quantum device, which is the storm, just does it. It doesn't calculate the fingerprint, it simply is the thing that has the fingerprint. It measures itself, what the machine actually did.
Okay, that's genuinely gorgeous, and I don't want to lose that. The quantum machine isn't outthinking the classical one, it's just being the very thing the classical one is struggling to imitate.
You've put your finger right on it. It's the difference between predicting the weather and simply being the storm. The supercomputer is trying to forecast every raindrop. The quantum chip is the sky. Of course, the sky finishes first. It isn't doing arithmetic at all. It's just weathering.
But, and I feel this coming a mile off, a fingerprint of a random storm is useless, isn't it? Nobody wanted that pattern. It doesn't say anything. It's not a factored number. It's not a molecule. It's not a message. It's just proof that the storm was too complicated to fake.
And there it is. You've walked yourself straight to the truth that the headline left out. Yes, the task was chosen precisely because it's hard for a classical computer and natural for a quantum one, and for no other reason. It has no use. None. It designs nothing, decrypts nothing, discovers nothing. Researchers even have a slightly sheepish name for this kind of job. They call it sampling. The whole point was to find a task where the quantum machine could plant a flag and say, "Here is something I can do that the classical world finds desperately hard." It's a benchmark, a proof of principle, a demonstration that the beyond classical territory is real and that a real device can set foot in it.
So it's a bit like building a car that wins one drag race on a custom track built specially to suit it. And then the headline says, "Cars have replaced walking."
That is almost exactly right, and I'm going to keep that. It won the one race it was built to win, on the track it was built to win it on. That's a genuine engineering achievement. Don't let me talk you out of that. But it cannot yet drive to the shops. It cannot carry the groceries. The task it beat the classical world at is not a task anybody needed doing. And the leap from "can win this one contrived race" to "the future has arrived, every secret is crackable." That leap is where the hype lives, the whole distance of it.
The scientists called it a big name too, didn't they? I remember a word.
They did, and the word caused no end of trouble. The original word was supremacy, quantum supremacy. Meant narrowly, the moment a quantum machine does something, anything, that's beyond the practical reach of any classical machine. A technical milestone. But the word is enormous. It sounds like dominion, like the old machines have been dethroned across the board. So a lot of people now prefer the cooler phrase quantum advantage, or plainer still, beyond classical. Same milestone, less swagger. And honestly, the swagger is most of what went wrong in the telling. The mountain that kept getting shorter.
All right, hit me with the other shoe, because you keep saying the headline left things out, and I can feel there's more. What about the 10,000 years? That was the number that did the damage. That's the number that made it feel like a different world.
That number did not survive. And the story of how it fell is my favorite sober lesson in the whole subject, so slow down with me here. That 10,000 years was not a measurement. Nobody ran a supercomputer for 10,000 years. It was an estimate, the team's best guess at how long the best-known classical method would take to fake that fingerprint. And the moment they announced it, they had, without quite meaning to, thrown down a challenge to every clever classical programmer on Earth.
Oh no, you told the world's best coders that a mountain was unclimbable.
Which is the surest way in the world to get it climbed. And climbed it was. Within days, a rival group showed that with a cleverer use of ordinary computer memory, spilling the calculation onto hard drives instead of cramming it into fast memory, you could bring 10,000 years down to a couple of days.
Wait, from 10,000 years to a couple of days? Just from a smarter way of using the machine you already had?
Just from that. And it didn't stop. Others brought fresh mathematical tricks, clever ways of tracking only the parts of the quantum storm that matter for the fingerprint and throwing away the rest. The estimate kept tumbling, down to hours. In some later analyses, ordinary good computers could match the thing outright. The mountain that was supposed to take 10,000 years to climb turned out to have a footpath up the back. And each time somebody looked, it got shorter.
So the headline number was What? Wrong?
Not wrong on the day it was said. It was the honest best guess against the methods known at that moment. But it was fragile, and that's the thing to carry home. The classical baseline is not a fixed wall you clear once and forever. Every time the quantum side plants a flag, the classical side sends its cleverest people to plant a flag right next to it, and very often, for a while, they can. So, beyond classical is not a finish line you cross and win. It's a moving frontier. The quantum machines keep getting a little bigger and cleaner. The classical algorithms keep getting a little smarter, and the border shifts back and forth.
That's not the picture I was sold at all. I was sold a moment, a before and after, the day the world changed.
There was no such day. There was a genuine milestone, wrapped in a number that was far too dramatic and far too brittle, sold as a revolution that hadn't happened. And I'd rather you have the true shape of it, a hard-fought, shifting frontier, than the clean, false line. What it really proved, and don't be a cynic either.
Okay, but now I'm worried I've swung too far the other way. If the number collapsed and the task was useless, was the whole thing just nothing? Was I fooled twice, once by the hype, and I'm about to be fooled again into thinking it was empty?
Thank you for asking that, because it's exactly the right correction, and I don't want you to leave here a cynic. Cynicism is just hype wearing a frown. The same laziness, refusing to look closely. So here's what did happen, and it's worth respecting. A device built by human hands took 50-odd of the most delicate objects we can make. These qubits, so fragile that a whisper of heat destroys them, as we agonized over a few episodes back, and held them in a coherent, entangled, interfering superposition, all together, cleanly enough to produce a pattern that genuinely strains the classical world to fake. That is not nothing. It's a landmark in control. The first time we built a quantum system elaborate enough that brute force simulating it is a serious fight, even for our best classical machines. Everything in this series, the qubit, entanglement, interference, demonstrated working together at a scale nobody had reached before.
So the achievement was real, it just wasn't the achievement in the headline.
Precisely. The real achievement was, we can now build and control quantum weather this elaborate. The headline achievement was, quantum computers now do useful things faster than any other machine, and the world has changed. The first is true and hard won. The second is not true yet. And the space between them is where you and I are going to live for the rest of tonight. Because that space has a name, and it's the honest name for where we actually are. The noisy era we actually live in.
Give me the name. Where are we actually standing, right now, in this whole story?
We are in what one thoughtful physicist named the NISQ era. An ugly little word, but honest. It stands for noisy, intermediate scale, quantum. And every word is doing real work. Backwards. Quantum. Yes, real quantum machines, real qubits, real superposition and entanglement, not simulations. Intermediate scale, tens of qubits, in the best machines, a few hundred, maybe reaching toward 1,000-ish now. Not the handful of the early days, but nowhere near the numbers the dream needs. And the first word, the important one, the one the headlines forget.
Noisy.
Noisy. And that word is the whole crisis we lived through a few episodes back, come back to collect its debt. Remember the enemy, decoherence. Every qubit is in a screaming argument with its environment. Every stray photon, every tremor of heat, every imperfection is the world reaching in and measuring the qubit a little, smudging its delicate superposition, dragging it back toward a dull classical 0 or 1 before you're done using it.
And I remember the cruel part. The very sensitivity that makes a qubit powerful is the same sensitivity that dooms it. You can't have one without the other.
You remembered the knife's edge exactly. So now put that together with a computation. A real quantum algorithm, Shaw's, say, the codebreaker, isn't a few gates. It's a vast, deep sequence of them, one operation after another, thousands upon thousands deep, each one a rotation of these delicate arrows. And here is the killer. Every single gate is a fresh chance for noise to creep in. Every operation is another whisper down a game of telephone.
Oh, and a game of telephone garbles after only a few whispers.
After only a few. So on today's noisy machines, you can run a shallow circuit, a few layers deep, and get something meaningful out before the noise eats it. But go deep, run the long algorithm, and by the time you reach the end, your beautiful quantum state has dissolved into random hash. The signal drowns. The interference pattern you were so carefully arranging, the whole point, the thing that makes the wrong answers cancel and the right one ring out, it gets washed away into mud before it can form. That right there is why we can't yet do the thing in the headline. Why today's machines can't run sure.
So let me say it back plainly, because I want to be sure I've got the real reason, not a fuzzy one. It's not that today's machines are too small to run Shaw's algorithm and crack the internet's encryption. It's that they're too noisy. They'd fall apart halfway through.
It's both, braided together, but you've got the heart of it. Size alone isn't the wall. Even if I handed you enough noisy qubits tomorrow, the computation to factor one of the big numbers guarding the internet is so long and so deep that the noise would shred the state long before you reached an answer. You'd get mush. Reliable mush, delivered quickly, but mush. The machine we'd need isn't just bigger. It's a fundamentally different kind. One that doesn't drown in its own noise. A machine that can correct its errors faster than it makes them.
And that, error correction, that was the rescue. The whole triumphant chapter. Spread one good, logical qubit across a whole crowd of physical ones and keep watch on the errors without ever looking at the data itself.
The rescue, exactly. And it works. The theory is sound. We walked through it. There's a threshold. Get your physical qubits just good enough, below a certain error rate, and then piling more of them together makes the encoded information more reliable, not less. The errors start cancelling out faster than they accumulate. That's the promise that saved the dream. But, and here's where tonight's honesty bites hardest.
There's a but the size of a house, isn't there? I can hear it in your voice.
The size of a house. Two of them, actually, and the first one is the overhead. A qubit is not a qubit.
Overhead. This is the how many physical qubits does it cost to make one good one thing. You gave me a number last time and it made me wince.
It should make you wince. It's the single most important number for cutting through the hype, so let me plant it firmly. To build one logical qubit, one qubit good enough to compute with reliably, one that error correction keeps clean through a long computation, you don't need a couple of physical qubits. You need somewhere between hundreds and thousands of them, all working together, all being watched, all correcting each other. Call it 1,000 to 1, roughly, for the hard jobs. 1,000 fragile physical qubits to make one trustworthy logical one.
1,000 to 1. So when I read a headline that crows, "New chip hits 1,000 qubits,"
you should immediately, quietly, ask the only question that matters. 1,000 of which kind? Because if it's 1,000 noisy physical qubits, which it always is today, then in the coin that actually buys you computation, that might be worth roughly one logical qubit. Maybe not even that. The headline number and the useful number are separated by that 1,000-fold wall. It's like judging a car by the horsepower in the brochure, when what you care about is whether it can finish the race without the engine flying apart. The brochure number is real. It's just not the number that gets you anywhere.
So all these qubit counts everyone's racing to announce, bigger, bigger, bigger,
Are real, and they matter, and progress is genuine. but a raw physical qubit count is the horsepower on the brochure. It is not the count of usable, error-corrected, logical qubits. Not remotely. And the day someone announces even 100 good logical qubits, all correcting their errors, all computing together reliably, that will be a far bigger day than any supremacy headline, and it will probably get a fraction of the coverage because it won't come with a number as juicy as 10,000 years.
All right, now do the code-breaking machine, the full dream. Shor's algorithm, actually cracking the encryption that guards the whole internet, in logical qubits and then in real physical ones. How far is that from a few hundred noisy qubits?
Take a breath, because the gap is the whole point. To run Shor's algorithm against one of the big numbers that locks down today's internet, you'd need on the order of a few thousand logical qubits, the good, clean, error-corrected kind. Now multiply by the overhead. Thousands of logical qubits, each built from hundreds to thousands of physical ones.
And you land in the millions.
In the millions of physical qubits. One well-known estimate landed at something like 20 million, running for the better part of a day. And, being scrupulously honest, that number isn't fixed either. Clever people keep arguing it downward as methods improve, toward a million, with speculative schemes dreaming of far less. But even the optimistic end, a million physical qubits, set that beside the few hundred, maybe low thousands, in the biggest machines that actually exist today. A 1,000-fold gap at least. That is not a gap you close by next quarter. That is not, we're almost there. That is a chasm, and everyone honest in the field will tell you so.
A few hundred against a million. When you say it like that, the "are we there" from the top of the show sounds almost funny.
It's the right thing to feel. We are standing on one rim of a canyon, and the useful machine is on the far rim, and in between there is a very great deal of the hardest engineering our species has ever attempted. That's not despair. It's just the honest scale of it. The good news, honestly earned.
Okay, I need you to throw me a rope here, because you've walked me right up to the edge and now I'm feeling the drop. 2 episodes of noise nearly killing the dream, and now a canyon 1,000 times wider than where we're standing. Is there real hope in the true version, or only in the hype version?
There is real hope, and I wouldn't be doing my job if I let you leave without it. The honest kind, the only kind worth having. Because here's what happened recently, and it's the genuine article. For years, error correction was a beautiful theory nobody had actually shown working the way it's supposed to. The whole promise, remember, is that below the threshold, adding more physical qubits to protect the information makes the logical error go down. More is better. That's the magic claim. And for a long time, in real hardware, when you added more qubits, the extra noise they brought swamped the extra protection, and things got worse, not better. The theory said, cross the threshold and it flips. Nobody had cleanly crossed it.
And now someone has.
Recently, yes. A team took a patch of physical qubits arranged as a single logical qubit and then made the patch bigger. More physical qubits guarding the same one piece of logical information, and watched the error rate. And for the first time, cleanly, convincingly, the error went down as the patch grew. Make it bigger, it gets better. Roughly halving the error each time they stepped the patch up a size. That is the threshold theorem, the thing we pinned all our hope on a few episodes back. Caught in the act, working in real hardware, for real.
So the rescue isn't just a chalkboard proof anymore. Somebody actually saw the errors bend downward.
Somebody saw the curve bend the right way. And I cannot overstate how much that matters, quietly, underneath the noise of the headlines. It's the first solid evidence that the road across the canyon is a real road, and not a mirage. That if you keep scaling, keep improving the physical qubits, keep piling them up in these protective patches, the thing genuinely does get more reliable rather than less. It's one logical qubit, mind you, or a small handful, not the thousands the dream needs. It's the first plank of a bridge that has to be 1,000 miles long. But it's a plank laid on solid ground, and before this we mostly had faith. Now we have a plank you can stand on.
That's the shape I trust, actually. Not we cross the canyon, just the first plank holds.
The first plank holds, and that's worth more than any 10,000-year headline because it's true, and it's load-bearing, and it points the right way. Why the smart people disagree.
So then, how long? Come on, first plank's down, the road's real. When do we actually get across? When's the useful machine? Give me the number.
And now I have to do the thing I promised you at the start of this whole season I would always do, even when it costs me the tidy answer. I don't know, and more to the point, nobody knows, and the people who tell you they know are the ones you should trust least. This is the second great honest fact of the night. The smartest, most informed people in this field, looking at the very same evidence, disagree with each other by decades.
Decades? Not is it 5 years or 7, actual decades of disagreement among the experts.
Decades. You'll hear serious, credentialed people say a useful, error-corrected machine, one that does something worth doing that no classical machine can, is perhaps 10 or 15 years off. And you'll hear equally serious, equally informed people say 20, 30, or we genuinely cannot say because we don't yet know if the engineering scales the way we hope. A few sober voices say we may never reach the very biggest dreams at all. And they're not disagreeing because some of them are foolish. They're disagreeing because the honest error bars are just that wide. Forecasting the arrival time of a solution you don't yet have isn't science. It's weather guessing, decades out.
But the roadmaps. Every company puts out these glossy roadmaps with dates on them. This many qubits by this year, error correction by that year. Those look awfully confident.
They do, and read them the way you'd read any ambitious plan from a team that very much wants your investment. As aspirations, not prophecies. Even the sunniest industry roadmaps mostly point to the end of this decade for the first genuinely useful, error-corrected demonstrations. And first useful demonstration is a long, long way from a machine that cracks the internet's encryption. The rope bridge with its first plank is not the 8-lane motorway. So when a headline hands you a confident date for when quantum computers will change everything, ask, says who, and what are they selling? Not out of cynicism, out of the plain adult knowledge that the error bars are wide and the incentives to sound certain are enormous.
That's the episode 6 lesson, wearing a new coat, isn't it? The hype inoculation one.
The exact same needle, and I'm glad you felt the jab. Back then we inoculated you against the biggest myth, that a quantum computer tries every answer at once and magically solves everything hard. Tonight, it's the timeline version of the same disease. The myth that the useful machine is just around the corner, sold with a confident date. Same cure both times. Look closely, ask what's actually being claimed, and be just as suspicious of the breathless salesman as of the sneering cynic. They're the same failure of attention, one grinning and one frowning. What it will be good for first.
All right, let's say the bridge does get built. First plank's down, and let's be hopeful the rest follows, over whatever number of years nobody can name. When we finally have a real, error-corrected, useful quantum computer, what's the first honestly good thing it does? Not the marketing, the real first job.
Now this is my favorite question, because the honest answer is also the most beautiful one, and it's been hiding in plain sight since the very beginning of this whole idea. Think about what a quantum computer is. It's a machine made of quantum stuff that naturally does quantum things. Superposition, entanglement, interference, as its native language. So what is it going to be best at? What's its home turf?
simulating other quantum things, modeling quantum systems, using quantum to understand quantum.
using like to model like. And that was the original dream. Before code breaking, before any of the flashy stuff, the very first person to imagine these machines imagined them for this. Nature isn't classical. Molecules, materials, chemical reactions, at bottom, they're all quantum. Electrons in superposition, entangled, interfering. And that's exactly why they're so murderously hard to simulate on ordinary computers. An ordinary computer chokes on all those amplitudes, the same monster we keep meeting. But a machine that is quantum can hold a quantum system in its own quantum guts and just let it play out. A wind tunnel for molecules built out of the same kind of stuff as the wind.
Give me a concrete one. What's a real thing that would actually help?
Chemistry and materials, above all. Imagine understanding exactly how a particular molecule holds itself together, where every electron really wants to be, so you could design a better catalyst. There's a famous one, the natural process that pulls nitrogen from the air to make fertilizer. Nature does it gently, in a little clump of atoms inside certain bacteria. We do it industrially, in a brutal, energy-hungry way that eats a serious slice of the world's energy. If we could properly simulate that natural clump, really model its quantum guts, we might learn to copy nature's gentle trick, and that alone would be a gift to the planet. New battery chemistries, new materials, maybe even the endlessly promised room-temperature superconductor. Better medicines, designed by understanding the molecule rather than guessing and testing. That's the plausible first prize, not because it's flashy, but because it's the machine's native tongue.
Okay, that I believe, and it's lovely. What about the ones I hear about constantly? Quantum computers revolutionizing finance, logistics, traffic, artificial intelligence. That's most of what I actually see in the news.
And here I have to be the sober friend again. That bucket is mostly labeled optimization, finding the best arrangement out of a staggering number of possibilities, the best delivery route, the best portfolio, the best schedule. And it's seductive, because those problems are worth real money, so the marketing is loudest exactly here. But the honest scientific picture is far cloudier than the ads. For most of these everyday optimization problems, we do not have a quantum algorithm with a proven dramatic speed-up. Remember episode 6, the speed-ups we actually know how to get are special. They need particular hidden structure, the kind factoring has, the kind quantum chemistry has. Generic, find me the best schedule problems mostly don't have that structure, and for them, the quantum advantage is, at best, modest and unproven, and at worst, entirely absent. A lot of the quantum will revolutionize your industry noise is a hope dressed up as a fact.
So when a company tells me they're using quantum computing to optimize their supply chain, today,
Hold on to your episode 6 reflexes. Today's machines are noisy and small. They can't yet beat a good classical computer at any real-world money-making problem. Not one, not yet. Much of what's marketed as quantum optimization right now is either running on classical machines with a quantum sticker on the box, or it's an experiment that a laptop could match. The genuine proven advantage, the one we can point to with real confidence, lives in simulating quantum nature herself. Chemistry, materials, physics. That's the promised land we can actually see. The rest is a landscape of maybes, some of them honest and exciting maybes, but maybes, and you're owed the word maybe out loud. The sober middle, changing the locks early.
I have to come back to the scary one though. Episode 5 gave me a genuine chill. Shaw's algorithm, the thing that could crack the encryption protecting basically everything. My bank, my messages, the whole internet. You've spent tonight telling me the machine that could actually do that is 1,000-fold away, maybe decades, maybe never. So, do I stop worrying? Is the chill cancelled?
Here's the grown-up answer. A lovely example of holding two true things at once without panicking or shrugging. First, no machine that exists today can break that encryption, or will next year, or, almost certainly, for a good many years. So no, don't lie awake tonight. And also, the world's security experts are, right now, quietly and sensibly changing the locks. And they're right to.
Both at once? Nothing can break it, and yet we're already replacing it. Why on earth rush if the threat is decades off and maybe never?
Two good reasons, and neither is panic. The first, changing the locks on the entire internet is slow. Many years to design new codes, agree on them worldwide, and roll them out to every device and bank and website. If you wait until the burglar is at the door, you're already far too late. You start early precisely because it's a decades-long job. The second reason is subtler and genuinely a little chilling. A patient adversary doesn't have to wait for the quantum machine to exist. They can harvest your encrypted secrets today, copy them down, scrambled and unreadable, and simply store them. Sit on the hoard for 10, 20 years. And then, if a code-breaking quantum machine ever does arrive, unlock the whole lot at once, retroactively.
Oh, that's nasty. Steal it now, read it later. So anything I want kept secret for the next 20 years is already at risk, even though the machine doesn't exist yet.
Harvest now, decrypt later. That's the actual name for it, and it's the one genuinely sensible reason to act with some urgency. So the good news, the sober middle good news. The world already saw this coming. Standards bodies have already chosen and published a new generation of encryption. Codes built on mathematical problems that we believe even a quantum computer can't crack. It's called post-quantum cryptography, and the switchover has already begun, out of sight, in the plumbing of the internet. Not out of panic, out of the plain prudence of a locksmith who changes the lock before the burglar is known to be on the way.
So the honest headline isn't, the internet is about to be cracked, and it isn't, nothing to see here. It's, the machine that could crack it may be decades off, or may never come at scale, and precisely because we can't be sure, the careful people are calmly upgrading the locks now.
You just wrote the only responsible headline in the whole subject. Keep it. It's got room in it for both the real risk and the real distance, and it doesn't sell you either terror or a shrug. That's what the truth usually looks like, less exciting than either extreme and far more useful. Why the truth is the best story.
You know what's strange? I came in tonight braced to have the magic taken away from me. It's all hype, the Emperor has no clothes, put your toys down. And that's not where we've landed at all.
No, and I'd have failed you if it were, because that would just be cynicism, which we agreed is only hype with a frown. Let me gather up where we actually are, all of it in one breath. We can now build and control quantum systems elaborate enough to do something no ordinary computer can easily fake. Real, new, in our lifetimes. But the dramatic numbers around it were brittle, and the beyond classical frontier is a living fight, not a finish line. We live in the noisy era. Small machines, no full error correction yet. Unable to run the great algorithms because the noise still shreds them. The overhead to build good qubits out of fragile ones is brutal. Hundreds to thousands to one. And the useful, code-breaking machine sits 1,000-fold across a canyon. But the first plank of the bridge was recently laid on solid ground. Error correction, for the first time, seen bending the errors the right way. The timelines are honestly unknown, the experts disagree by decades, and anyone who's certain is selling something. The first real prize will most likely be chemistry and materials, the machine's native tongue, not the flashy optimization the ads shout about. And the sensible people are already, calmly, changing the locks.
When you lay it all out like that, It's less than the headline promised, but it's so much sturdier. I feel like I could actually stand on it.
Because you can. And that's what I most want you to walk out with. A revolution that's genuinely underway does not need to be exaggerated. The exaggeration is what you reach for when you're afraid the real thing isn't impressive enough. But the real thing is impressive enough. Building a machine that computes in the language of nature herself, wrestling the most delicate objects we can make into holding still long enough to think. That story doesn't need a fake 10,000-year number bolted onto the front. The truth of where we are is a better story than the hype because you can trust it. You can build on it. You can hand it to someone else without walking it back next year.
Information is physical. That's been the thread the whole way through, hasn't it? And tonight it almost turns into a warning. Because these machines are made of the physical world, the noise, the cold, the fragility, the brutal engineering. And that's exactly why the dream is so hard, and why we can't just wish it into being with a press release.
That's the whole of it, and you found your own way there. Information is physical, so quantum information lives or dies by real, stubborn physical things. Coherence times, error rates, temperatures a hair above absolute zero, millions of parts that all have to work. The physics that makes the dream possible is the very same physics that makes it hard. No magic exemption. And the people doing this honestly know that better than anyone. Down in the cold, fighting the noise 1 qubit at a time. The last people you'll catch promising you the moon by Tuesday.
So where does that leave us for next time? Because it feels like we've come all the way down to the machinery, the cold, the noise, the engineering, the least romantic place in the whole series. And I know you well enough by now to know you don't end a season in a fridge.
No, I don't end a season in a fridge. We've spent 11 nights coming down into the machine. The bit, the qubit, the gates, the noise, the wires, the cold, the honest hard state of the art. And next time, the very last night, we turn around and climb all the way back up, past the machines entirely, to the strangest and grandest idea this whole journey has been quietly walking toward. Tonight we said, information is physical, and we meant the noise and the cold and the fragile qubits. Next time, we ask the question that turns the whole series inside out. What if information isn't just physical? What if it's the thing the physical world is made of? What if the universe at the very bottom isn't particles and forces at all, but information? And everything else, matter, energy, even space itself, is written on top of it.
From erasing a single bit and warming the room, all the way to the universe being made of bits.
That's the summit. That's where we've been climbing to since the very first night. And it's exactly where I'll meet you, one last time, at the top.
The whole way down into the cold, just so we could turn around and see how high we'd actually come. All right, take me up. Next time. Good night.